Today's conversation is about how do particles exchange neighbors and the whole fabric evolves during deviatoric loading. So imagine several particles subjected to loading, and we would like to anticipate the relative motions and some statistical trends as they evolve towards failure. Well, we can extract one of the particles and represent the other particles by springs that are contacting the particle and applying different forces onto it. So this will be the case if there are other particles around, in this case, this particle. Now, that particle is in equilibrium. That means that all the forces acting on the particle add up to 0, and that means that the summation of forces in x is equal to 0, and the summation of forces in y is equal to 0. Furthermore, these forces are not only normal and going through the center, in the case of a sphere, but they will also be forces at angles. So don't think of these springs going towards the center. They will also be summation of moments in this case. That will have to be equal to 0 for the system to be in equilibrium. If some action moves one of these particles, then an unbalanced force will excite this particle. In other words, there will be a force that is resulting from the summation of forces that is not equal to 0. And if there is a force, then there will be an acceleration is equal to the force over the mass. And if there is an acceleration, there will be a displacement, if it starts at rest, will be equal to 1/2 acceleration times a delta t squared. Therefore, we are going to, an unbalanced force will create an acceleration, creates a displacement, and the particle will move. But now if the particle moves, it will contract some springs and extend others, and the system will be again out of equilibrium. Furthermore, a change in this force will cause a change on the force acting on the other particle, which was initially at equilibrium. And so there will be a perturbation that will propagate throughout the system until the system reaches equilibrium once again. This is numerically implemented in software that fall under the name of discrete element methods, originally contributed by Peter Candle in 1971, 1979, a classical paper. But the concepts were already in the physical chemistry community under molecular dynamics. It's also Newtonian mechanics. What is unique about particle scale analysis in the context of sense is that the interaction between particles is going to happen through springs, and those springs could be, for example, nonlinear springs, because there is a Hertzian contact that, as you may remember, is a nonlinear force deformation. Like a helical spring, when you apply a force, it behaves nonlinearly. By comparison, molecular dynamic simulations uses the van der Waals forces and the Coulombian forces to take this into consideration. Now that we have this very powerful software, we can begin running analysis to see how does a soil mass evolve as we apply a deviatoric loading towards failure. And because every particle will have a normal force and a shear force and a series of contacts around them, then we will have a large number of values that will come out of the numerical simulation. And in order to visualize them, we are going to use some form of statistical measurements. And this is what we do next. Coming out of discrete element simulations, we can see how many contacts are in different directions. So I look at contacts that are between 0 and 2 degrees everywhere in the system, and I add them up. And then between 2 degrees and 4 degrees everywhere, and I add them up. And now I can make a polar histogram of contacts, and it will tend to look something like this. So in each direction, here I have the number of contacts in direction theta. Now I can also go and look at all the particles that have a contact in it at 20 plus or minus 1 degrees, let's say. I look at what is the normal force, but now all these normal forces are going to be different. So one way to go about is to plot the average normal force in each direction. And so this will also look like a peanut. And in this case, this is the average normal force in direction theta, where this is the angle theta. At each contact, there will also be shear forces. So let's say once again that I look at all the contacts that are with a contact normal at 20 plus or minus 1 degree. I look at all the shear forces and I plot the average shear force in contacts at 20 degrees. And so I will have one more plot, which is going to look surprisingly like this, where at any direction, this value here is the average shear force in contacts at a certain direction theta, where this is theta. So let's summarize. This is the number of contacts in a given orientation within a range. So it's a polar histogram. This is a polar plot of mean normal force in contacts that are taking place in a certain orientation. And this is the mean shear force in those contacts. Now, think of this as an elongated ellipse, but you can also think of it from a Fourier approach, that this is a circle, and if I draw a circle here, quasi-circle, then you see that at theta equals 0 is less than a circle, at theta equal 90 is more than a circle, and there is a waviness going around the circle, so I can approach it as a Fourier series in this polar plot, and I'm going to say that the number of contacts in direction theta is equal to a mean number of contacts, which is the radius of the circle, times 1 minus the amplitude of this oscillation, the amplitude for contacts, times cosine 2 theta. It has periodicity 2 theta because you see we have 2 complete cycles of cosine. I can do the same for the normal force. Imagine that there was a circle here, and once again there is a subtraction at 0, there is an addition at the top, and this means that the mean normal force in direction theta is equal to the mean value, which is the radius of the circle, times 1 minus the amplitude of that oscillation, the degree of anisotropy in normal forces, cosine 2 theta. And now for the last one, there is really no circle. It's just dying at 0, at 90, 180 to 70. And so the mean shear force in direction theta is equal to some amplitude, A of the shear force, times sine 2 theta. By the way, this plot corresponds to the case where I have like a triaxial test. I have subjected the specimens to isotropic confinement, and then I apply a deviatoric load. And if I see all the particles, how they are migrating and changing neighbors and changing the contact forces, and I plot this polar histogram or polar the mean values, this is what I would get. So look how interesting this is. When the sigma 1 is in the vertical direction, the prevailing number of contacts, the magnitude of the normal forces align to take that primary loading direction. And in that primary loading direction, there is zero shear. Shear is mobilized transverse to sigma 1 and sigma 3. It's in the direction of maximum shear. Now, if you go back to an earlier presentation on Mohr circle, before we drew the Mohr circle, we actually plotted the polar diagrams in the polar coordinates. We plotted the shear stress and the normal stress that would be required to preserve equilibrium of an element subjected to sigma 1 and sigma 3 if I chop off the element and I put equilibrating stresses on that plane, and they were looking pretty much like this diagram of normal forces and this diagram of shear forces. That was Mohr circle for the equivalent continuum, and this was normal stress and this was shear stress. What this is telling us is that the integral of the microscale response has to be the macroscale effect. In fact, in a beautiful conclusion by Leo Rothenberg and co-workers, he proved that the mobilized friction angle, the sine of the mobilized friction angle, which is how far we are approaching failure, is equal to the sum of these anisotropies times some coefficient, but will be AC plus AN plus AT. And there is a coefficient here. So this is a macro scale measurement of the mobilized friction angle at the macro scale, looking at the soil mass as an equivalent continuum. And this is a statistical summary of the evolution of anisotropy. Shear strength is all about the ability of the soil to mobilize internal anisotropy. Discrete element methods give us a wonderful opportunity to understand the behavior of soils at the particle level. In my mind, the key goal is not to simulate the whole soil mass underneath a foundation. For me, a key part of discrete element modeling is to understand soil behavior at the particle level, to feel as a particle. For example, one very important consequence of discrete element methods is to show that not all the particles are involved in carrying the load. In fact, if you color particles according to those that are most highly loaded, we see that there are chains of particles that are mostly responsible for carrying the load. And these are called particle chains. And these particles are not only carrying most of the load, but they do it in the direction of the external principal stress. Now, what is interesting is that the particles that are holding those chains and are preventing them from buckling are actually carrying a small load and is primarily in the transverse direction. So it's something like as follows. This would be one of the chains, and these are the particles next to it. These are carrying forces primarily in the vertical direction. However, these ones are holding the chain, preventing it from buckling. It's a very is a very effective way that nature uses to transfer load throughout the granular skeleton. Another important observation that we gain from understanding granular materials at the particle scale is to understand the deformation mechanisms. So, for example, one could be that one particle subjected to normal load and shear loads actually slide. So one would be sliding. The other one is rotation, but rotation is tricky because consider the following system of gears. Imagine that these are gears with teeth, and I impose a clockwise rotation on this particle. That means that this contact is going to move inwards, and therefore the particle at the bottom is going to move in this direction. That means that this contact will move downwards, which means that this particle is going to rotate downwards and around. This contact is going to move inwards, and the particle above will have to go in this direction. So from the particle on the left, this contact is going to move upwards, and the particle from the right is also moving upwards. So this is rotationally free. Now, what would be the situation if I have only 3 particles touching each other? Once again, imagine that they are like gears with teeth. And so if I force the upper one to rotate clockwise, this point will go towards the center, which means that the particle here will be counterclockwise. This point wants to go down. If this wants to go down, this is going to rotate like that. That means that from the particle at the bottom on the left, the contact here wants to go inwards. However, the particle from the top, it would like to go upwards. And now we are in trouble because this system cannot rotate. So from a rotational point of view, it's rotational frustration. You can readily see that rotation is more likely when the packing is loose than when the packing is dense. And so how does a soil deform and shear in this case? Well, it has 2 options. If it cannot rotate, then there will have to be slippage at the contact. And that is one possibility, sliding or slippage. The other one is that the packing may open up, and in the process of dilation, the number of contacts decreases and the rotational frustration decreases. So the other possibility is to dilate, so the coordination number decreases. Now, this is energetically very demanding because in order to dilate in a triaxial specimen that is subjected to confinement, if it wants to dilate, it has to push against the confinement. It has to do work, the work of expansion, of volumetric dilation. So this will imply work against the confinement. Now, slippage is also very energy demanding. That's friction. And so the soil has to make a choice, and nature will follow the path of least resistance, the weakest link. And so nature, or the soil mass as it deforms, it will be making this choice. Should I slip at contact or dilate to prevent rotational frustration? And the interplay between these choices is what gives rise to the critical state line. At high confinement, it's very difficult to work against dilation. Too much work, so it prefers to slide. At low confinement, it will be dilative. So now you can go back and review the analysis of deviatoric loading in drain and undrained loading of soils, and you will be able to explain why the critical state line looks the way it is. It's a function of void ratio. It's also a function of confinement. The next thing that we can begin explaining when we look at the particle level using discrete elements and particle scale analysis is the following situation. If I pour sand on top of a table from a funnel, eventually I form a cone at the angle of repose. This is the angle of repose that somehow resembles the angle of internal shear strength of the soil. But now let's do another experiment. Imagine that I have a cylinder, a shallow cylinder, I fill it with sand, and then I unplug it, I pull out the trapdoor, and it was initially filled with sand, and now I let the sand grains fall. This will also form a cone. In fact, to give some three-dimensionality, you can see the conical surface, and this is the cylindrical element. This is very easy to do, and you can convince yourselves of these results, which are very important. And so this is also an angle of repose, which we're going to relate to the friction angle. But notice the following: two grains that are deposited here at the surface, as they migrate outwards. This angle of repose is formed by divergent flow. However, two grains here that are coming from the top, as they migrate, they converge towards the orifice, and this will be an angle of repose for convergent flow. And when you do these experiments, you will see that the angle of repose in convergent flow is somewhere between 1 to 1.5 the angle of repose in divergent flow, or the friction angle in divergent flow. Interestingly enough, I can do also a triaxial test in which I confine the specimen, and then I apply axial compression, so deviatoric loading in the vertical direction, and this is going to get shorter and fatter. That means that there will be divergent flow of grains. So this is a typical axial compression test. However, if I do an extension test, and I can do an extension test in two ways. One is by axial extension, or the other one is by lateral compression. If I do an extension test and now I pull here, the specimen is going to get narrower and taller, and so flow is in such a way that convergent flow. So it would be an axial extension or a lateral compression test, and the opposite would be here, axial compression or lateral extension. And when we compare the friction angles between these two, in convergent flow, in extension test, friction angle in extension test is about 1 to 1.5 the friction angle in compression tests. This is really quite fascinating. From such a simple experiment of just measuring the angle of repose in these two situations, I get the similar friction angle anisotropy being mobilized. The implications are huge, but one thing that we can conclude is that in convergent flow, the coordination number tends to increase because particles are converging, while this is not the case in divergent flow. It's more complex than that, but it's a matter of particles coming closer together. Now, the implications are huge because if you remember, for example, the coefficients for the bearing capacity equations, Meyerhof, Prandtl's equations, the NQ and gamma, even the factor for NC, they are logarithmic with a friction angle. And it's not that we're going to miss in the friction angle by 1 or 2 degrees. The friction angle can change here from 33 degrees to 40 degrees. This is a huge effect, which has huge implications to stability analysis to factor of safety computations. So keep in mind, friction angle anisotropy depends on the loading conditions. I'll provide two more examples of important lessons that we can gain by understanding and observing the evolution of granular materials during shear. For example, we could have had packing of elliptical particles, and you can actually reproduce this at home by taking rice or navy beans, and when you shear them, not only contact numbers and the contact orientations will evolve, the normal forces will change, the shear forces will change, but in addition, now we can also talk about a histogram of particle orientation. And so after shear, you tend to see something that looks like this, and if you are shearing in the horizontal direction, particles actually look like if they were skiing on water at an angle. They are not perfectly flat because of the moment effects and the shear forces. The other example, so now if we study elliptical particles, and a very minute amount of ellipticity has a dramatic effect on the soil. So if we are going to summarize this, we're going to have 4 polar diagrams: the histogram of contact normals and the particle orientations, and then the polar diagrams of mean, normal, and shear forces. The other case is that if you have a soil that is cemented, lightly cemented, we are not talking about a sandstone, we are talking about a soil with some degree of diagenesis, or it has experienced wetting and drying, and some cement forms at the contacts, then this soil behaves quite different as well. And the reason is that during shear, it tends to break like in blocks. It doesn't totally degrade during early stages of shear. It tends to break as in blocks. So now if I zoom out and I don't look at individual particles, I look at the soil mass, we are going to see that it may have taken a blocky structure. I'm exaggerating the extent of blockiness, but the point I'm trying to make is that while each of the blocks, the particle arrangement inside each block may be quite loose, and you say, well, this soil has high void ratio, it will be contractive, because it breaks in this form, and because each block is interacting with the next one across these quasi-flat surfaces, now the structure is very dilative. So cementation may give us not only higher stiffness, it will also change the dilative tendency of the soil. That means it will shift critical state line. I will attach to the final page of these slides a few references where you can find examples for these different situations that I have described here today.